Thank you everyone for joining our webinar today. Today we are talking about the 3D printing applications with HP Jet Fusion 3D printers and Lubrizol TPU. This webinar is brought to you by Hawkridge and our partners in digital manufacturing. My name is Savannah and I will be part of your host today as Robin had some computer technical issues. Today we are joined by two experts in their field. Is Ed Thomas from Lubrizol Advanced Material. Ed is a marketing professional specializing in additive manufacturing for Lubrizol Advanced Materials, one of the largest global producers of thermoplastic polyurethane. And Mark Mariano from HP, who is the product manager for the HP 4200 and 5200 series. He has an extensive application knowledge in automotive, medical, and manufacturing industries on the HP Jet Fusion series. Today's agenda, we're just going to talk a little bit, we're going to talk about the HP Jet Fusion 4200 3D printers, where Mark will talk about, that'll be Mark, and then Ed will dive into the Lubrizol TPU, and if time permits, we'll have the Q&A. All right, and I am going to pass it over to Mark so that he can share. All right, and Mark, I'm passing it over to you.
All right, so I hope now it's well set up. Awesome, great. I'm close here. Sweet. So, well, yes, as Savannah said, my name is Mark. I work for HP pretty much in the early beginnings. Back in 2016 is when we launched the technology HP Multi-Jet Fusion. And most likely, probably you already know and you heard about it. But I'd like to make maybe a quick refresh because I think it's a very unique technology that is worth the while to make sure that we all understand what it is and what are the differences among other 3D printing technologies. So when we launched this technology back in November 2016, we launched it in a way that we wanted to be really disruptive on the industry. And that's what we have been focusing pretty much since we launched it, and as well for the years previous to that one that it took us to develop this technology. Basically, HP Multi-Jet Fusion has three main value propositions. The first one being full functional parts. Our parts are isotropic, are really strong, and up to some level of degree are rivaling current injection molded parts. That's one of the main value propositions. The second one is the speed of printing. We can be up to 10 times faster than any other 3D printing solution today in the market. And that's thank you our single pass printing. We basically can print as many parts as we fit in a layer or in a bed without changing the time that it takes to print those. And I'm going to explain how this can happen. And the second one is, and the third one is the lower cost of producing our parts. We can be really, really cost effective when we compare it with other 3D printing technologies. And the reason why we are so cost effective is mainly driven by two. One is a lower cost of material, which can be as low as $30 per kilogram, depending on, of course, obviously on which material and which system you have. And the second one that drives the cost down is the high reusability of our materials, being our materials reusable up to 90%, some of them, but being all of them, all the ones that we have, but 80% reusable, which actually leads to less waste and more reuse of non-fresh powder, which at the end ultimately is driving the cost down significantly. So our printing process works in 4 steps. I'm going to be highlighting those 4 steps now. The first one is the printing. We are actually a powder-based technology, and we print on top of powder. There is no layers involved in this printing technology. It's a matter of applying agents, fusing and detailing agent on top of the powder bed. Those agents are applied by printheads. Printheads that are industrial printheads, similar to the ones that you will find in a web press that is printing today, for example, books, but at an industrial level. And of course, we modify them so they are very high heat resistant. But we can apply those agents that you see on the right through those printheads on top of the powder bed, shaping a section of the object that we want to produce. how big or small are those droplets will tell us how precise is that part going to be, right? If we print one droplet that is extremely large, we're going to have less accuracy into printing that part. So here is where we have a very disruptive technology, because we can print with the same accuracy that we can print today in photos, in books, because basically we are leveraging the same core technology that HP is known for more than 30 years. Our drops as small as 9 picoliters, which basically for us to understand means that in a bottle of 1 liter of water or 1 liter of agents, there will be 9 trillion droplets of agents. So basically meaning that if we take 1 millimeter, with 1 milliliter of agents, we can place 9 billion different drops across the bed. It's very, very precise, and this is what allows us to have a very high accuracy while printing parts on top of this powder bed. The second process of our technology is basically fusing those parts, right? And basically where we have placed those agents, when we apply heat, those agents will create a reaction with the powder, and the powder will melt. And the rest of the powder that has not received those agents will not melt, and it will be ready for reuse. 100% of that powder can be reused. This heat that we just explained are applied mainly by 2 different types of lamps. One are the top lamps. We have 20 top lamps on top of the case of the printer that are applying constant heat into the whole chamber. And then we have fusing lamps that are in the carriage that is moving back and forth on top of the printer, on top of the powder bed, and they are together with those printheads. So basically, while the top lamps are constantly applying heat, the fusing lamps, they apply heat precisely when the carriage is moving and they are applying the agents. These fusing lamps, they apply the additional heat that the material needs to melt, but it will melt just where those agents have been placed. All the other powder will remain fresh and non-fused. Third step is being able to control with a very high precision where we melt and where we don't melt. And as I explained, this is mainly driven by our printheads and the agents that tell us where we want that part to melt and where we don't want that part to melt based on where we apply those agents. But we also have a real-time thermal camera, which is what you see on the left, that as you might see, I'm leveraging the same picture as before because the thermal camera is next to the top lamps. This thermal camera captures 5,000 points of real-time heating control, and basically we can change how much heat do we apply in each individual section of those top lamps, and we can also define how much agents do we apply on the powder bed based on the behavior on what the camera is reading. Meaning, if we are seeing that the part is getting really warm because either it's very thick or has other parts that are really big next to it and there is start having heat transfer, that camera will read it and will tell the fusing lamps or the heating lamps to lower their power or increase their power, and will also tell the printheads whether we should apply more or less of those agents. So we basically have a consistent fuse across all the print bed, across all the parts. And this is happening real time at every single layer of the print bed. This basically is what achieves to have a very high accuracy and very high repeatability in our systems. The fourth point is material management. Basically, our technology is extremely clean. It's a combination of the printer, which is what you see on the left. Then we have a build unit, which is that loop fill trolley that is on the right, and then we have the processing station. So what we're basically doing here is that build unit is what holds the part and what holds the material, and it's shifting between printer and processing station back and forth, allowing the printer to focus on printing, so you never stop production, and allowing the processing station to do what it's meant to do, which is cooling down the parts and filling back that build unit with powder. So basically, if you have two build units, you can keep printing back and forth non-stop, because while one build unit is printing on the printer, the other can be cooling down. And that's one of the key benefits as well of our technology, which is the high throughput that our systems can offer. Having a quick look to our portfolio, that's our global portfolio as of today. We have the 500 series and 300 series, which is our entry low volume prototyping systems that print black and white and full color. Then we have the 4200, which is our mid-level production, is where today we have certified the Lubrizol TPU that Ed is going to be sharing with you in a few minutes. And then we have the 5200, which is the new model that we released back in May last year, which is our most productive system. So we differentiate this between 500 and 300 series being on the low volume production and prototyping, and the 42 and 52 systems being focused on the high-end, mid to high-end volume production. And then, of course, we have metal jet that is our metal technology. To give an idea of productivity, right? I created this example with Magix. Well, you most likely all know Magix will have to work with it. This is a brake lever for a motorbike. So basically, what I try to do is printing a full job and see how many I could fit. So to give you an idea, these are, I think, 290 parts per build we can print in a 4200, meaning that in a just single build, we can fit 290 parts of those ones. And we have a productivity that allows us to print 2 builds per day, meaning that we can deliver 580 of these parts in a day, just with one printer, and a very, very low cost. If somebody's interested in knowing the cost, I'll let you ask a question later. This is another example, for example, of one of our customers. Actually, their name is Apit. It's a great company. What they've done is they developed a frame for a face shield, and of course, they're trying to design it in a way that we can produce more parts, and it's also very cost effective. So in just half a build, they can print 144 of those parts. And the half a build will take somewhere in between 5 to 6 hours to print. So imagine how many you can print on a full day. These are some of our customers. I think that it's important not just back up your just say things. It's also important to back up them with images and examples of successful customers. So we have Forecast 3D, which is a digital manufacturer. They started our journey with us back 3 years ago with one machine, with one 4200. I think it was like 6 or 8 months later, they saw the value and the disruption of this technology, and they purchased a few more. And today, I believe they have somewhere between 25 to 35 of these systems. They are fully digital manufacturer. They get parts on time, on real time to customers across the United States and beyond. And they are a true successful case of how a company can transform and be totally digital. This is another case of another customer using HP multi-jet piston. In this case, this is Smile Direct. You probably heard about. They produce the dental aligners for customers across the states. I think I lost count how many do they have, but I'm pretty sure it's above 80 the machines that they have, and they are fully in-house production in real time of these dental aligners. That everyone is unique, so they use many systems to bring the hundreds of thousands of dental aligners that are needed for their business. Pretty much among the last slides, this is our material roadmaps. As you might have heard, we don't develop exclusively our materials for our technology, and a clear example is having today Ed from Lubrizol explaining the Lubrizol TPU. But what we do is basically we collaborate with companies across the globe, and they develop those materials for the technology. So as of today, we have the P11, the P12, the glass bits. All these are HP certified materials and developed by HP. We also have the Vestocin from Evonik, and we also have the Lubrizol, the S-stained M95A from Ed. All of them certified for HP Multijet Fusion 4200 series. This is a new material that we released at the end of last year. It's been very successful for our customers, and I'm very happy that Ed is joining with us today to share with you a little bit more about this elastomer. So with that, I hope you all stay safe and that you learned something today, and I'll give the chance to present to Ed. Thank you.
All right, thanks, Mark, for that information. I think that came out great. With that being said, I'm going to go ahead and turn this over to Ed Thomas so he can dig into the Lubrizol portion of this webinar.
Oh, thank you, Mark, for the introduction. Thank you, Robin. Let me just make sure I'm sharing the appropriate screen. Yep, awesome. Okay, thanks a lot. So I am Ed Thomas. I am the North American 3D Printing Business Development Manager for Lubrizol Advanced Materials. And I'm here to talk today about S-stained 3D TPU M95A. That is our powder TPU now available for the 4200 series of HP MJF printers. I'll just be referring to the material as M95A throughout the majority of the presentation. So briefly, I'll talk about the Lubrizol Corporation. I think everyone here is familiar with Hawkridge. They're obviously hosting the webinar. HP has a fabulous global household brand name, but Lubrizol is traditionally a business-to-business company, so there's a lot less familiarity with us. I'll talk very generally about what is TPU, why customers would traditionally use a TPU, and then I'll spend the bulk of the presentation talking about M95A, what applications we think this material might be suitable for, what some of the functional properties of the material are, because a lot of people here today likely already have applications in mind, and then what it's like to actually process this material and post-process this material. So first off, with the Lubrizol Corporation, we are a Berkshire Hathaway company. That is to say, we are one of Warren Buffett's companies, and that's proved pretty advantageous, especially recently, being that we are a financially strong and stable partner for the people that we do business with. But it has also provided us a certain amount of leeway in being able to pursue innovative paths, which is how we first became involved with 3D printing. So about 2/3 of the business revolves around Lubrizol's traditional role with creating additives for oil additives, with about 1/3 of the business being Lubrizol Advanced Materials. That is the polymer business, and that's where the 3D printing business unit is. The company does about $7 billion a year in revenue and has just under 9,000 employees globally, split between North America, Europe, Asia, and a very small presence in Latin America. So I did mention that we are a large player in the TPU industry globally, and that's a bit of an understatement. We operate 8 major production facilities for TPU globally in North America, Europe, and Asia. Currently, our 3D printing powders, such as the powder, the M95A, are developed in Brecksville, Ohio, about 20 miles south of Cleveland, with resins for 3D printing filaments developed outside Barcelona, Spain. We're also in the process of developing a 3D printing center of excellence in Songjiang, China, in Asia. So what is a thermoplastic polyurethane or a TPU? And it's a thermoplastic elastomer. And the way Lubrizol traditionally describes this is that it's a material that bridges rubber and traditional plastics. That is to say, it's often soft and flexible like a rubber, but can be processed and reprocessed similar to a thermoplastic. So all TPUs are composed of three components: a polyol, an isocyanate, and a chain extender. And by changing the type of these components and the way in which the TPU is formulated, you can end up with a huge amount of distinct material attributes. So currently Lubrizol offers in the area of about 1,200 distinct TPUs offering different performance benefits. So it's incredibly versatile material. And the reason that I bring this up is that TPUs captured a lot of attention recently on a lot of different 3D printing platforms. And while they are all TPUs, they are not necessarily comparable materials. They can all offer really different performance characteristics. So the user needs to be very aware of what they're getting. So why do customers traditionally use TPU? And there's a multitude of reasons, from abrasion, impact, or puncture resistance to the hardness of the material. So currently Lubrizol offers TPUs in the range from 52 Shore A, that's about the hardness of a rubber band, all the way up to about 85 on the Shore D scale. That's about the hardness of a construction worker's hard hat. So a really broad array of how rigid these materials can be. But there's a lot of other reasons, including the ability to dissipate static, antimicrobial properties, flame resistance properties, or the ability for the material to remain flexible in cold temperatures. There's a really wide array of reasons why people use TPUs. And what do they use TPUs for? So TPU can be injection molded, blow molded, extruded as a film, or even extruded as a fiber for use in high-end athletic garments, things like yoga pants. You can actually, some yoga pants, the elasticity and the stretch from them will come actually from TPU fibers. But in addition to that, there's a lot of use for end-of-arm robotic tooling, seals and gaskets. Midsoles for athletic shoes is a very common use, as well as things like paint protection films or the interiors of cars. A huge array of reasons why people use TPU for traditional manufacturing, some of which are relevant to 3D printing, many of which are not. So now that I've talked a bit about who Lubrizol is and what TPU is in a general sense, I'm going to spend the rest of the presentation talking about M95A. And the first thing I want to talk about is the roadmap that took us from initially stating that we wanted to develop this material all the way to the commercial release of the material. So it was in late 2017 that we originally partnered with HP to develop a TPU for the MJF line of printers. The material was not commercialized until late 2019. And the reason I bring this up is that I think it says a lot about Lubrizol's efforts to deliver a safe, reliable, and consistent product, but also just how rigorous the certification process is for materials appearing on HP's line of printers. I think customers can be assured that there was a rigorous process and quality materials are making it to the end user. So that was a 2-year process. We likely could have launched a commercial powder in late 2018. We entered initial beta testing with our TPU material, and while it was a commercially viable product, the feedback was that it didn't quite offer the end user the post-processing solutions they were looking for. So we actually went back, reformulated the material, and ended up launching the final product a year later at the end of 2019. And I really think this is a testament to our desire to release not only a commercially viable product, but the most user-friendly product possible. So what is M95A? And currently it is the only TPU available for the 4200 series of MJF printers. It's actually currently the only elastomer available, although I don't know if that will always be the case. It's a hard, flexible thermoplastic material with a Shore A value of 95, but I'll explain in a minute why we think that Shore value in durometer is maybe less relevant in 3D printing than it was when talking about traditional manufacturing. The material offers excellent elongation and flexibility with superior abrasion resistance, especially when compared to a lot of the other elastomers on other 3D printing technologies. It's also certified for skin contact applications in accordance with ISO 10993-5 and -10. On top of that, it has an 80-20 recycling rate. That is to say that in every build, 80% of the material is recycled, with 20% of the powder being first use or fresh powder. And lastly, I think the thing that we're most proud of is the ease of which this material can be processed and unpacked, which I'll explain more on later. So I did mention that durometer is less of a relevant attribute than maybe it was for traditional manufacturing. And we believe a lot of that is due to the fact that with 3D printing, you can achieve a very high level of complex design and print things that enables the printing of things like lattice parts that offer the end user radically different properties than just what the material itself can deliver. So a solid printed block might be 95 Shore A, but that feather on the right that was successfully 3D printed, obviously no one who picks up and handles that 3D printed feather realistically thinks that that is a 95 Shore A material. Obviously that's not a practical functional part, that's just a good representation of the design freedom that allows customers to get a wide array of performance characteristics out of their materials. So how does M95A stack up against the other materials on the MJF 4200 series of printers? And the answer is that it's not an apples to apples comparison. The nylons that currently appear on the 4200 printer are excellent materials. They are very dimensionally accurate, they are very rigid, and they are very strong with great tensile strength. But they are simply less flexible and offer significantly less elongation at break than a comparable TPU. So we don't see this as necessarily TPU competing with the nylons that are on the printer. This is simply a broadening of the portfolio of products that are available on the 4200 series of printers. A lot of the applications that are suitable for nylon are not suitable for TPU, and a lot of the applications that are suitable for TPU could not have been accomplished by using PA12, PA12 glass bead, or PA11. So I did mention applications on the previous slide. So where do we think this material is likely going to be used, and where have we seen it used already? And this is it's a general purpose material. That said, combined with the freedom of design offered by MJF printers, we think that there is a really wide array of applications where this material is suitable. Everything from external medical devices, such as soft insoles for diabetic patients, components for footwear, or recently we've seen face masks becoming more prominent, and that the mask actually can flex with the wearer's face and makes the prolonged wear of a mask significantly more comfortable. We also see applications for consumer goods with things like protective gear that takes advantage of lattices. We do believe that TPU latticed structures can provide significant benefits for things like impact absorption when compared with the foams that they would be replacing, as well as electronics cases that can provide levels of vibration dampening for the protection of sensitive electronics, but also industrial manufacturing, jigs and fixtures, anything that is prone to repeated abrasion and say rough handling in an industrial setting. TPU is an ideal fit for that. And as well, I'll talk about this more later, but with the temperature performance of this material, we do think that automotive applications are open, everything from flexible hoses to bellows that need compression and elongation on a routine basis. So I just put that up on the screen. I know there is a lot of skepticism in the 3D printing industry as to whether footwear is really ready for prime time. And I don't know, I can tell you that I wore those shoes for a week during a trade show, and those are obviously not even a prototype, those are a pre-concept piece of footwear, and they were remarkably comfortable and actually durable. So we are looking forward to seeing what footwear designers can accomplish with our material. So I'm going to move on and talk a bit more about the functional properties of M95A. I suspect a lot of people in the audience obviously know what industry they're in. They already have potential applications in mind, and they're curious to know if M95A is a suitable fit. So I'm just going to walk through some of the properties and some of the testing that's been done to M95A. So bear with me, I'm going to show a video here. The video does not have any sound, so your computer speakers are not broken, but it's just an illustration of material testing of M95A. So this is testing of elongation until break of M95A, which is kind of the barometer for which a lot of elastomers are measured. And we see exceptionally high levels of performance for elongation.
Hey, Ed,
Yeah.
do you guys have a specific method for testing these products?
We do actually, and afterwards the video that is, as the video shows, you can see in the footnotes the specific test methods that were used if users want to figure out how this data was gathered. It's also contained on our TDS that can be distributed to anyone interested after the webinar.
Thank you.
Yeah, no issue. And then abrasion resistance, this is something that's not necessarily the most exciting to look at, but a lot of elastomers often have relatively poor abrasion resistance properties. We believe this is an area where our material performs very, very well. This compression set testing, this is something we think is very relevant to the development of things like protective gear. If you were designing lattice structures for either cushioning or in the use of helmets, compression and the ability for the structure to regain its shape after compression is something that is significantly important. And this is something that's interesting. This is temperature performance testing. In a lot of cases, traditionally, TPU would not have a higher temperature performance than nylons. In this case, we see actually very good temperature performance from our material that I'll talk about in a bit. Okay, so we just looked through the video and some of the performance characteristics associated with M95A. The rebound testing that appeared on screen is specifically relevant to the footwear industry in most cases. But another test we were not able to capture on video was the Ross Flex test, which is something that is, again, very applicable to the footwear industry, but I think does show the robustness and durability of our material in a general sense. So the samples you see on screen were actually flexed to 60 degrees for 150,000 cycles at both -6 degrees Celsius, so below freezing, and 23 degrees Celsius, so about room temperature. And both the parts made it through with no cracks, damage, or failures. And this really does, while this might be applicable mostly to the footwear industry, it is a testament to how robust this material can be while remaining flexible. So I know in the video we'd illustrated what it looks like when our material is brought up to 200 degrees Celsius, and I just want to elaborate on that a bit more. So we have done or begun doing performance testing of our materials in increased temperatures. And you can see on the screen that up to about 250 degrees Fahrenheit, there's very little to no loss in properties for tensile strength or elongation at break of M95A. We do start to see a loss in properties beyond that point, but this was a 240-hour test, so this is a 10-day test. So we are very happy with the temperature performance of this, especially compared to other TPUs. And we really think that this opens up this material for use in things like the automotive industry for certain applications. Something that I consider to be even more impressive than the slightly increased temperature performance for a very long period of time was the ability of our material to withstand significantly increased temperatures for shorter periods of time. So on the screen is illustrated what happens when the material is brought up to 200 degrees Celsius or just under 400 degrees Fahrenheit for up to 18 hours. And again, while you see a decline in material properties, specifically tensile strength, the material itself does survive and it remains structurally it is intact, which is really impressive for a TPU. And we've already seen this impact things, certain applications like the ability to produce certain industrial fixtures. There was an industrial application that required 3D printing of a factory fixture that would be exposed to really high temperatures during an annealing process. And it made sense to 3D print these parts. Other materials were melting before the 200 degrees Celsius mark, and really high temperature plastics were cost prohibitive for the specific application. And our TPU was certified for use as that part, which is something that is really interesting and not something we predicted early on, but we are very happy with the temperature performance of our material. So, and the last thing I want to talk about for performance attributes is the hydrolytic resistance of this material. This doesn't necessarily relate to a specific application. This relates more to the environment in which a lot of 3D printed parts happen to be used. A major issue for a lot of TPUs is that they might not be hydrolytically stable. So M95A was exposed to 90% relative humidity for 8 weeks with minimal to almost no loss in observed tensile strength. So we can consider the material hydrolytically stable. I know I used to live in Georgia and those summers were miserable. So I do understand how important the ability of parts to survive in increased relative humidity is. And now I want to talk about one specific application. So I'm going to talk about what this is, why it made sense to 3D print it, and then why it made sense to 3D print in TPU. So this application was designed and produced by Forerunner 3D, a small service bureau and engineering firm out of Michigan that does really excellent work. And this part specifically is an industrial fixture for handling chrome door handles for the automotive industry during assembly. It fits on a rotary dial machine and handles the the chrome door handle as it is affixed to the rest of the door. So why did they want this part 3D printed? And the first answer is speed. These parts can get to the customer very fast. They can get to the customer really rapidly, especially given the iterative nature of the automotive industry. That made a lot of sense. But these parts are also limited run, and it didn't make sense to spend the money on tooling for all of these parts. Traditionally, they would have cast urethane these parts, but that does cost 2 to 3 times the amount that this 3D printed part cost. So in a general sense, it made sense to 3D print for this specific application. And why did they select TPU for this application? There's a few reasons why. The first is that TPU out of the multi-jet fusion printer platform is remarkably dimensionally accurate. This allows for a good fit of the chrome part into this fixture during assembly, just for the purpose of a consistent manufacturing process. But the material is soft enough that it won't mar or damage the chrome finish of the part before it is fixed onto the door. In combination with that, the material is abrasion resistant enough where it can survive tens of thousands of cycles without losing tolerance. So it's the combination of being soft and abrasion resistance that allows it to keep its accuracy and be useful when handling chrome parts. So this is a really good illustration of an industrial fixture that makes sense to 3D print, and it makes sense to 3D print in TPU. So talked a bit about applications. I'll move on to talk about what it's like to process this material through a 4200 printer and what the post-processing experience is, because that's an issue for a lot of elastomeric 3D printing products. So material processing, and the first thing I need to say is that this material was designed with the intent to make as user-friendly a product as possible. If someone is familiar with printing with an MJF 4200, likely nylon 12, we wanted the experience with the TPU to as closely resemble that operator's experience with the PA12. And we think we've been able to accomplish that remarkably decently. So first, the packaging is exactly similar to PA12. It comes in 30-liter and 300-liter packaging. We are currently working on bulk packaging, although we don't have a timeline for delivery. Printing time is slightly slower than PA12. We're looking at about a 19.5-hour build for a full build of M95 TPU. That said, the packing density is again very similar to what users are already used to, with a packing density suggested between 7 and 8%. And then there is the 80-20 refresh rate, which is similar to what people are used to with PA12. That is 80% of the powder is recycled from a previous build, with 20% of the powder being new during each print. Now, the thing I want to talk about next is the unpacking, which is often an issue for a lot of elastomeric 3D printing products. So when heated, a lot of elastomers have the habit of becoming what people describe as tacky or sticky. So the powder has the habit of adhering to itself in clumps or adhering to the 3D printed part. So it doesn't really matter if you can 3D print a very complex lattice shape. It's really of no use to anyone if you can't remove that 3D printed part from the powder in a cost-effective manner. And we think we've developed a powder that comes very close to simulating the unpacking experience of PA12. So I'm just going to show a quick video of what that looks like. For anyone familiar with the printing process, I really think this is a good testament to what it is like to work with our material. So again, there's no sound, you're not missing anything here. But if you're familiar with unpacking 3D printed parts, this is a pretty good experience. The powder is pouring out of the lattice structures. He's able to flex the parts. And there's not a huge amount of labor-intensive work to depowder what is a very, very large lattice structured object. So we think that is a good testament of what our material is like to work with. Okay, and the last thing I'll talk about is post-processing of M95A. And again, this is made to really closely simulate the experience people have when working with other materials on the MJF platform. So there's no difference in process when it comes to bead blasting this material. No special blasting cabinet is required. The normal tools that are in the shop are perfectly acceptable when working with M95A in most cases. Again, dyeing, most of the dyes we've seen in circulation in North America are perfectly compatible with M95A TPU. There's a couple exceptions out there, although we are perfectly happy to make the recommendation on what dyes are optimal and what dyes are preferred. A lot of coating solutions are also compatible with M95A. The issue is that a lot of coatings, surface coatings that are currently in existence are designed for rigid structures. And while they might successfully adhere to the TPU, the part then either loses its flexibility and there was no reason to print in TPU to begin with, or the coating is a habit of cracking or flaking off of the printed part, which is also not a great sign. So we're in the process of developing a proprietary flexible coating solution that will adhere to the TPU substrate, provide some level of surface smoothing, and flex with the 3D printed TPU. Surface smoothing is another issue. There's a lot of kind of commercially available surface smoothing solutions. We are currently exploring all the options available and hope to have some commercialized solutions in the near future. And the last thing I do want to talk about, especially recently, is the sterilization of this material that's come up a lot recently simply due to the COVID-19 pandemic, and I understand that. But we are currently experimenting with sterilizing the material with basically all the available or commonly used methods of material sterilization. If you have specific questions on if a chemical can be used to sterilize TPU, please reach out to us and we'll try and get you a good answer on that. And then I do want to talk about the material is safe for skin sensitization applications in accordance with those ISO standards. I do need to say that the material is skin sensitization safe if the user goes and applies a different surface coating onto the material or uses a very aggressive solvent to try and surface smooth it. That might change the skin sensitization ability of the final 3D printed part. So that's just a caveat there. People need to be cognizant of what they are putting on their printed part after it's been 3D printed. So, and this is just a little illustration of the flexible coating solution that will be available for TPU. It's currently in the beta testing phase, but it's a way of providing vibrant colors, some level of surface smoothing, and a flexible spray coating that adheres to TPU and actually flexes with the material, which is really amazing to see, actually. So with that, that is the final slide I had for the presentation to talk about M95A. We are always happy to answer any inquiries about the material and are happy to talk about M95A with any potential customers. I do ask that if you have a specific inquiry about the printer or the printer solution specifically or the upgrade process, please contact Hawkridge. They are the solution provider for the actual printers themselves, but we'll be happy to talk through M95A with anyone that's interested. And with that, Robin, I'll turn it back over to you.
Thanks, Ed. That was really great information. The content from both of our presenters today was fantastic. All right, guys. Well, if any other questions do just come in, I will make sure to address them directly. But I just wanted to thank everybody again for attending this webinar today. If you have any other questions outside of this that might arise, please reach out to me directly. You have an email address and you have a direct phone number for me, and I am prepared to answer any questions. Once again, thank you, everybody, all presenters, all attendees. Have a great day.